First, I want to thank the Fetzer Foundation for organizing this beautiful conference and for inviting me to participate in it. The plan of my talk is as follows. First, I will discuss my meeting with David Bowman, my interaction with him, and then I will tell you about my new approach to interference phenomena, and in particular, the two-slit experiment. How did I meet David Bohm? I was an undergraduate at the Technion, and I took a course in quantum mechanics. My instructor was Nathan Rosen from the Einstein-Podolsky-Rosen experiment. And at the end of the course, we are supposed to write a short work, and I came to Professor Rosen and told him that I'm interested in working on quantum theory of measurement. And he told me, no, young people should not work at all on something like this. You should try to do some down-to-earth physics problem. But I told him, Professor Rosen, the only reason why I'm doing physics is because I'm interested in deep questions, and I would like to work on this kind of problem. And he did not agree with me, and we had a problem because I insisted I want to work on foundations, and he did not allow me to do that. And I had an instructor, Gideon Carmi, who told me that there is a new professor that just arrived at the Technion, David Bohm, and I should go and talk to him. So I came to his office, knocked on the door, entered, and I told him about my ideas of quantum theory of measurement. He liked it very much, and he said, okay, I would like you to be my PhD student, and that's how we started to interact. And this was a marvelous experience for me, because we had so many things in common. We both felt, for example, that our own experience is really a physical experiment on the most complex system in the world, which is our brain. And therefore, if physics of today is not able to answer questions like what is becoming, what is free will, then something is missing in physics of today. And we agreed that there should still be a future physics that will be able to answer all these questions. Anyhow, we interacted very, very nicely together, and my thesis existed of three parts. The first part has to do with some ideas that I had about problems of measurement theory when you try to incorporate the restriction to velocity of light. For example, if you try to measure the momentum, you have to introduce a large uncertainty in position. But you can't do it very quickly because the maximum velocity of the particle is the velocity of light. So there is a limit then how quickly we can measure the momentum, and he agreed with me, and that was the first part of my thesis. And I have an interesting story to tell about that. Bohm was invited to visit Niels Bohr Institute in 1958. And he took me along with him. And when I was there, I met assistant of Niels Bohr, Or Peterson. And when he heard about my ideas, he said, I think Bohr would like to hear about it. And he arranged a meeting between me and Bohr. There was a small room for the meeting. I and Bohr were sitting near a blackboard, and the audience were Or Peterson and David Bohm. And I started to tell Niels Bohr, Professor Bohr, I have some ideas concerning quantum theory of measurement and the problem with the velocity of light. And Niels Bohr told me, wait a minute, I want to tell you something. And he gave me a whole hour lecture on all his ideas about complementarity and quantum theory of measurement. At the end, he said, that was a very interesting conversation. He got up and left the room. This was an unbelievable experience. The only way I can explain it is that Niels Bohr had so much feeling against Bohr, Bohm, that because I was a student of Bohm, he didn't want to listen to me. It was unbelievable. I came out from that room with a long face, and people asked me what happened. I told about this experience, and then said, oh, we have to tell you something that will comfort you. A few years ago, Feynman came to tell Bohm about his ideas of doing the trajectories and superpower difference, and Bohm told him, no way to speak about trajectory in quantum mechanics, gave him a whole hour lecture why one should not do it, and left the room. So I felt much better after that. Now, the second part of my thesis had to do with the idea of David Bohm, that there was an experiment done by C.S. Wu in which he looked at this integration of positronium to two photons, and she looked at the correlation of the polarization of the two photons to tell what was the angular momentum of the positronium. And David Bohm told me, I believe that this could be a way to check whether the EPR correlations exist or not. So I analyzed this. This was a very complicated calculation, the most complicated calculation I ever done in my life. And we concluded indeed that all classical way to look at this correlation does not work. So this was in fact the first experimental test for Bell's inequalities, much before Bell did his work, but people did not realize that we have done this work. I remember I came to talk about it in the physical conference in Israel. Nobody was interested in it. I talked to Rakach, who was the leading physicist in Israel at that time, came to his house, told him about this work, no interest at all. It was unbelievable how people did not pay any attention to this problem at that time. So I was very discouraged, and from then on I only talked about the AB effect and never mentioned this at all, and only later people got interested about it when Bell came out with the general proof that it cannot be done. We have only used the most simple example how you can try to analyze it classically, and it did not work. Anyhow, I had beautiful experience in my interaction with David Bohm, and until now I'm so happy for my lack of meeting him. I have to tell you a secret. As you know, those of you who follow my research, I never write any article by myself. I have no talent in writing things. Bohm realized it very early, and all the articles that we wrote together was written by him. This was the beginning of the tradition that I never write anything by myself. Not only that, I will tell you a secret. When Bohm saw my struggle in trying to write my thesis, it took me a whole month to write the first 2 pages, he took upon himself to write my thesis. I think I'm the only example in the world where the thesis advisor wrote the thesis of his candidate. So I am feeling safe that I can talk about it now because I have 2 doctorates from Bristol, the regular doctorate and honorary doctorate, so I can't take my doctorate now when they hear that Bohm wrote my thesis. Okay, so now I come to the main part of my talk. I believe that the problem of the interpretation of quantum mechanics is due to the fact that the whole quantum mechanics was analyzed in the wrong way from the beginning. What do I mean by that? You know that quantum mechanics started in 2 separate directions. First came Heisenberg with his metric formulation, and this was at first led to a very nice answers about the harmonic oscillator and hydrogen atom, but the minute when they tried to do a more complicated problem, it was very, very difficult mathematically. Then came Schrödinger, and the approach of Schrödinger that followed the Broglie idea was so nice mathematically that people assumed that because of that, that is the best way to approach quantum mechanics, the wave picture. But the wave picture from the beginning was the wrong idea. Why? De Broglie said that because in the electromagnetic case we have the classical wave, and then the particles which are the photons, later what's called photons, then the body said it must be the same thing for the particles. Classical particles must also have wave properties. But what the body did not realize, and all the other people that followed him did not realize, is the fact that in the electromagnetic case, an individual photon does not have any wave property, because the wave properties have to do with electric and magnetic field, and the electric and magnetic fields are complementary to the photons. So in order to have wave properties, you must have a large number, in fact, uncertain large number of photons. So individual photon does not have wave property, and therefore individual particle does not have wave property, if the analogy is correct. And indeed, when you look at the Schrödinger representation, you write the vector in Hilbert space as superposition of amplitude psi of x times eigenstate of position. That amplitude psi of x can never be measured when you have just a single particle. Because you look at two different psi of x, they are not corresponding to orthogonal vectors, and therefore they cannot be checked experimentally for a single particle. You can check psi of x only when you have an ensemble of particles. So if we want to understand the reality of a single particle, we have to look for something else, not for psi of x, which cannot be observed for individual particles. So here comes Heisenberg picture for our aid. Let me show you how in the Heisenberg picture you can follow the reality of individual particles and see the interference phenomena in a completely different way. So what is the Heisenberg approach? Heisenberg says that we have to look on particles by looking at observables which are functions of position and momentum, and we have to look at these functions, how they change as a function of time. These are the metric formulations of Heisenberg. And we can ask the following question. If we have a vector in Hilbert space, we can characterize this vector not by its coefficient of expansion in positional representation as Schrödinger done, but we can ask the question, what are all the operators A, N, which are the observables, for which the vector psi is an eigenvector? This is the opposite question of the usual one. Usually we say, given an operator, what are all the eigenfunctions of the operators? Here we ask the question, given a vector in Hilbert space, what are all the operators for which this vector is an eigenvector? Why? Because if we look at only this subset of operators, we can measure them without determining at all the vector. If we can show that the set of all eigenoperators completely characterize psi, then by following their evolution, we can find out what happens in time to a single particle. Now, indeed, if we look at this, all the set of operators, they completely define a single psi. Let's see a simple example. Suppose I have just a simple Hilbert space of 4 dimensions, and look at the vector 1, 0, 0, 0. I ask, what are all the Hermitian matrices for which this vector is an eigenvector? These are all the matrices that have arbitrary entrance here, 0 here, 0 here, and anything here. If we look at all these operators, this is an eigenvector for these operators. And this is the only eigenvector. Anything else will make some of these matrices not eigenmatrices. Therefore, by following these matrices and following the time evolution, we can see exactly what is the time evolution of the vector, and we can follow it by discussing really properties of an individual particle. So let us see what does this operator tell us about the most important thing, which is quantum interference. So suppose I have a 1 dimension, and I have a vector in Hilbert space, which in the Schrödinger representation is a superposition of two wave packets that have no overlap. 0 here and two vectors, one here, superposition of one here and one here. And suppose I look at the vector psi alpha of x, which is the superposition of psi left of x plus e to the I alpha psi right of x. This is really the situation what happens when a particle comes through two slits. Now let me show you that any operator which is just a polynomial in position momentum will not be sensitive to alpha. For example, if I look at the average of p to the n for this state, that average will take the nth derivative of this function and multiply it by this one. When I calculate the average, I will get 0 because there is no overlap even of the nth derivative of this times that. That means that the average of any polynomial does not depend on alpha at all. So if we look for an eigenoperator for this equation, we have to look for something which is not a polynomial in position momentum. What is this something? If I look at the operator e to the I PL over h bar, where L is the distance between the two of them, the average of this will obviously depend on alpha, because e to the I PL over h bar take this one and bring it to here. So the average of this operator will be e to the I alpha over 2. So what is this operator? This operator depends on the momentum in a way that if I change the momentum by integral times h over L, the operator does not change. That means that this operator depends on what I call the modular momentum. How do I erase here?
Up there. To the right. Up, right.
Oh, yeah, I didn't see it. Thank you. So I define P modulo H over L, which is P modulo P0. P0 is H over L. Then if I look at this operator, P modulo P0, it's this operator as a function of momentum. This modular momentum is the thing that does depend on the relative phase. And it's very important to realize that if I try to expand e to the I PL over h bar as a sum of p to the n over n factorial times the right parameter, this expansion is the Taylor expansion of the function, which is the superposition of the two wave packets. This Taylor expansion doesn't work because obviously the derivative here cannot tell me anything of what happened here. So we cannot explain the behavior of e to the I PL over h by looking at the powers of momentum, because that will be the Taylor expansion, and the Taylor expansion cannot tell us what is the relative phase. So this operator, the modular variable operator, is independent of the usual kind of operator that we are familiar with. And it's this operator that is relevant, this observable, that is relevant for interference phenomena. So we must look what happens in interference phenomena if we try to follow it by looking at the time evolution of the Heisenberg variables. We have to look for the difference in behavior of this kind of variables classically and quantum mechanically, because that can be the only way to explain the interference phenomena when we talk about things that can be observed in individual particles. Listen carefully. I am saying that we can follow the whole time evolution of these wave packets when they spread in time and they come in overlap and produce interference phenomena. We can do it not by looking at what happened to the wave, but instead we look at what happens to those observables that we can observe on individual particles. So we must look for a different behavior for these observables, classically and quantum mechanically. This difference will not be due to uncertainty, because these things are definite. It will not be due to any disturbance. The difference can only be due to the difference between classical and quantum dynamics. So I claim that the main thesis of my claim is that we can understand quantum mechanically as due to the fact that the quantum equations of motion, the Hadamard equation of motion, differ in a fundamental way from the classical equation of motion when we look for the relevant function of position momentum which describe interference phenomena. So what is this difference? The best way to introduce the difference between commutators and Poisson brackets. The Poisson bracket is the classical equation of motion, commutator is the quantum equation of motion. Let's look at the following question. If I have a function of x and another function of p, I ask first of all, classically, when I consider Poisson bracket, is there any function of x and any function of p whose Poisson bracket is different from 0, is equal to 0, and the functions are not trivial? The answer is no, because the Poisson bracket is the derivative of f with respect to x, derivative of 0 with respect to p, and if the product of that has to be equal to 0, one of the functions has to be trivial. But if I look at the commutator equation, f of x and g of p commutator, then I find that if f of x plus L is equal to f of x, and g of p is equal to g of p plus p0, where p0 is h over L, these two functions commute. That means that the modular variables, if f of x plus L is equal to f of x, f depends on the modulo of x, and the same with p. Quantum mechanics tells us that there is a new situation here as far as the equations of motion are concerned, if we consider the difference between Poisson bracket and commutator. In other words, and this is the main idea, if I have an Hamiltonian, which is p squared over 2m plus v of x, and we look at the equation of motion ddt of e to the I p over p0, and we look at the equation of motion for this observable, if we look at it classically and if we look at it quantum mechanically. If we look at it classically, we see the Poisson bracket between this and v of x will be different from 0 only if the particle is at a position where the v of x is the derivative of v with respect to x is different from 0. Why? Because ddt of e to the I p over p0 classically is simply 1 over p0, I over p0, times dp dt times e to the I p over p0. So if dp dt is not equal to 0, then this function changes, but if it's equal to 0, namely if the particle is not in a place where there is a force, that equation of motion is 0. Quantum mechanically, ddt of e to the I p over p0 is equal to v of x plus L minus v of x times e to the I pl over h bar, or over p0. So here we see the fundamental difference between classical physics and quantum mechanics. In quantum mechanics, the time derivative of the relative variable, the modular momentum for interference, depends not only at the position of the potential at the position of the particle, but also the position L away. That means that the particle knows quantum mechanically. If in one slit, it knows whether there is a potential in another slit or not, because this equation of motion is non-local. This is the main idea. So the main idea is that if you look at the two-slit experiment, you can see, therefore, on the particle, that the particle actually moved only through one slit. You don't know through which, but moved only through one slit, and it knows whether the other slit is not open or not, because there is a non-local equation of motion for the relevant variable, that we can think about it as the property of individual particles. Now, when I first thought about this idea in the 1962 or 3, and we wrote an article that we called deterministic operators for two-slit experiment, I was unhappy about it for the following reason. First of all, you can immediately say that if the equation of motion quantum mechanics is known locally, it seems to violate causality immediately. Because if the particle moves through here, and if I open or close the slit here, that thing will change. That modular momentum will change immediately, then it will violate causality. How does quantum mechanics save the day? It saves the day because under this condition, where we know where the particle is, the modular momentum is completely uncertain. How do you see that? If I look at a particle, I know that it's localized only in this region of dimension smaller than L. If I look at e to the I Pn L over h bar, the average of that is equal to 0 for every n. Because that thing translates the wave function by distant L away, and the scalar product then is 0. That means that the average of e to the I P L over h bar times any L is equal to 0. That means that P modulo P0 is completely uncertain. It's like an angle on a circle that has equal probability for all values, and therefore, if you change it, you can't see the change because it's completely uncertain. That's how you save causality with this non-local equation of motion. But then I was unhappy because I said if each time when the particle goes through one slit, its modular momentum is completely uncertain, there is no way then to see what is the effect of this non-local equation of motion. And then the day was saved when many years later I realized that you can formulate quantum mechanics by using two vectors at any time instead of one vector. How do you do that? First of all, why is it relevant before I do the mathematics? The idea is the following then. I have the thing that goes through two slits, which are two wave packets. At the beginning, I certainly don't know through which slit the particle is going because I want to know the modular momentum. Then I wait for the interference pattern to happen, and after it happens, I can check whether the particle was coming from this side or coming from that side by a future experiment. So if I'm able to describe the situation at the present by two vectors, one coming from the future that will tell me through which slit the particle went, and one coming from the past that tells me that the modular momentum is definite, then I can see indeed the non-local phenomena and not violate causality because I can know only from the future through which slit the particle went. This is the basic idea, and now I will try to describe it a little bit more mathematically. So if this is time, in classical physics, if we know at a given time, at the initial time, the state of a classical particle, then any future experiment cannot tell us anything new because the classical physics is deterministic, and if I know completely the state at one time, there cannot be any surprise in the future. In quantum mechanics, if I know the state of the particle initially, I can still do an experiment at a later time and find the final state, phi n, which is different from different particles, although all of them started at the same state initially. So I can pick quantum mechanically on two boundary conditions, one in the past from past experiments, and another, a future boundary condition in the future. And then I can ask, what is the situation at the present? And if I do experiment in the present, I find, and that is the basis of what's called now the ABL formalism, a work that I've done in 1962 with Bergman and Leibovitz, where we use the vector coming from the past and the vector coming back from the future. We use them in equal footing in calculating the probability of what happened in the time in between. And it turns out that in order to see the effect of both vectors, you have to do in the middle what I call weak measurements. Because any strong measurement will either destroy one vector or the other. But if we do weak measurement, where the interaction with each particle is very, very weakly, we collect many, many cases that all of them ended up at the same final state, then we can see the property in the middle without any disturbance. So this is the fundamental idea. So let me now describe to you how to save the day with respect to the two-slit experiment. So here are two slits. Each particle comes separately with the same initial state of definite momentum in this direction. We get, in the Schrödinger representation, we get contribution like this. Here we see interference pattern. We see it only when we have an ensemble. So we assume that we have an ensemble of particles that all of them started the same way. What we are doing here now, we do weak measurement on each one of the particles that give us very little information from each particle. But when we collect the information from many particles, we can see the interference pattern. But the important thing is that the weak measurement on each particle doesn't disturb its state, hardly disturb its state. Therefore, after we do this weak measurement, we can do here still an experiment that will tell us whether the particle came from this side or whether the particle came from here, because we need to disturb the state by the weak measurement. So we see that in the present we can do an interference experiment that will show us that indeed somehow what we call the wave property somehow was relevant for it. But then we see by a future experiment that we know through which slit the particle went. If we know through which slit the particle went, this is not the usual explanation of interference. The only explanation for this interference is by looking at the properties of each individual particle, which are the eigenoperators. We look at how they behave. We see that each particle that went from here, that went through this slit, nevertheless had another property, which is the modular momentum, that dictated what interference pattern we will have here. And that modular momentum has the equation of motion that's non-local, that tells it whether this slit is open or not. Now, this is the most important thing I'm trying to bring through here, and I actually am willing to stop here for a minute and let you ask me questions, because this is the main idea. I'm not sure if it's clear to you, but the main idea is the following. We now say that each individual particle, we can follow its time evolution by looking only on things that can be measured in it without disturbing it at all. And yes, 1 minute. And therefore, if we don't disturb it at all, there must be another way to explain why the particle behaves as if it knows what happens far away from it, not by saying that something went through both places, but by saying the particle went only through one place, but it has also another property, which later translates to the interference pattern. That property is the modular momentum. That has no local equation of motion, and therefore it knows whether the other slit is open or not. And we know through which slit the particle went by a future experiment that doesn't violate causality now. If I say, if I close this, that modular momentum has changed, but I will know that the particle went through here only by a future experiment, so that cannot be used at all to send signals, okay? So, causality therefore demands that there will be uncertainty principle. So we can deduce uncertainty principle from non-local equations of motion. So my starting point is saying there is one axiom that tells you the difference between classical and quantum mechanics, and that axiom is that classical physics is local and quantum mechanics has no local equations of motion. That non-local equations of motion must insist, in order to save causality, that there will be uncertainty principle. Because if there were no uncertainty principle, I would violate causality if I have non-local equations of motion. So non-local equations of motion determine that there must be uncertainty principle, and it shows us now why, even though the particle goes always through one place, it knows what happens in other places because of these non-local equations of motion. Do you have a question?
I'm sure it's out of my ignorance, but if the particle is immediately having entered one of the, let's say, the slit below, you're claiming that it's aware of the other slit's presence?
I'm saying that if the other slit is open or closed, there is no different behavior of the modular momentum of the particle.
Okay. So,
Okay.
but there is no manifestation of that awareness before the overlap that we can actually show.
Yeah, the point is that if I assume that the modular momentum can be observed only later because I have a restriction, I'm not allowed to write an Hamiltonian that will involve directly the modular momentum in it because that will be no local. So the Hamiltonian, I can see only the effect of the modular momentum when it translates into modular position later. Okay, so only because I'm restricted here to do only local experiments, I can see the change in the modular momentum only later when it translates into different position representation.
I see. So you're because in the Bohmian picture, obviously the initial stages where there is no overlap is absolutely irrelevant as to the other.
No, but the Bohm picture says the Bohmian picture says that although the particle goes here, something goes also through there.
Right.
But I'm saying nothing goes through there.
No, okay. So having said that, then so afterwards, after having observed the particle in the interference region,
you don't observe it by strong experiment.
Right.
By weak experiment.
By weak measurement. Then you can assign to it a specific trajectory that shows that it was aware of the other one?
I don't speak about trajectories. No. I only say that if I look at the pattern for an ensemble of particles by weak measurement, I cannot tell what happened to each individual particle. I can only tell from the future that whether a particle went through here or through here, but that future experiment does not tell me a whole trajectory. If I know, for example, this was the mistake that Einstein and Bohm made when they tried to analyze the two boundary conditions. They said, for example, that if I know the momentum here, and if I later measure the position here, I have a trajectory in between, because I know the position and the velocity. But that is not true, because when you speak about weak measurement, you cannot speak about a strong trajectory, you can only speak about weak trajectory. If you know x and you know p, you don't know x plus p. Because when you try to measure x plus p strongly, you will destroy both vectors, okay? So you can only speak about weak trajectories, but not about strong trajectories.
I understand, but I guess what I don't understand is what is the difference in the behavior of the particle right immediately after the slits, immediately before the overlap? With the other slit open or not open? That's what I'm trying to understand.
If I look, for example, on a superposition of this plus that, and suppose I think the best way is to look at the example of interference in one dimension. That will be a way to simply answer it, okay? So suppose I have a one-dimensional problem. I start initially with superposition of two wave packets that move towards each other in the shading representation. Now, when they move until they finally meet here in the middle, and then I see interference pattern, and after that they left again, and one of them moves this way and the other moves that way. When they meet here in the middle, I do weak measurement on the ensemble, and then for each one of them later, I find whether it moves here or moves there. If I find that it moves here, I know that it was described all the time that by this wave packet. It doesn't mean that it had a definite trajectory, only that it was described by eigen operator of this individual wave packet moving. So I don't describe a definite trajectory. I just describe that the future boundary tell me that it was all the time that this wave packet. The past boundary condition tell me that it was the true position of the two.
Well, initially, so what you're saying though, that the wave packet on the right was aware of the presence of the other wave packet before they actually overlapped.
Say it again?
The wave packet on the right was aware of the wave packet on the left before they overlapped. That's the claim.
Yeah, but I'm saying that
yeah, okay.
if I look at the two
no physical manifestation of that. That's the problem I'm having. What is the physical manifestation that shows, that actually can prove that the particle and wave packet right was aware of the presence of the wave packet on the left before they overlapped? What is the physical manifestation as an experimentalist that I can look at?
Oh, okay. So the physical, if I do in the middle time weak measurements all the time, that tell me whether the particle is moving this way or that way,
also,
and then I do this weak measurement. I find that if I post-selection only those cases where the particle was moving from the right, the weak measurement in the middle will tell me all the time that the particle is moving only to the right. And the weak measurement will tell me that this case, nevertheless, shows interference pattern here. And I can explain that by saying that the particle was moving at the right and also a modular momentum whose equation of motion depends on whether I would do something here or not. And that I can demonstrate experimentally. So the lesson is the following. Heisenberg picture tells us that we can look at individual particles and say it has real properties, because I can do this measurement of a deterministic operator in principle. I can do it without disturbing the particle at all. So it's real properties. Therefore, if I can follow the time evolution, that by looking at real observables that belong to a single particle, I don't have to worry about uncertainty, about collapse, because I discuss only the deterministic experiment. Nevertheless, following this operator can tell me the whole story about the interference. How does it do it? It does it by discussing observables for the particle that differ fundamentally in their behavior classically and quantum mechanically. By the way, the operator e to the I PL over H bar, when I go to the classical limit, when H goes to 0 and L is finite, that operator still has no local equation of motion, but it's unobservable because it oscillates very, very fast. If H goes to 0, the P modulo P0 is unobserved classically. So you can say that the classical limit still have no local equations of motion, but they are for observables that cannot be seen. That's how you go to the classical limit in that language. So quantum mechanics introduces, therefore, new kind of variables that have no classical limit. These variables have no local equation of motion, and this no local equation of motion is the thing that explains interference phenomena on individual particles. When you look for ensemble, then you can think about the wave function as a property of the ensemble. You can measure psi of x if you have an ensemble of particles. But you can't say that psi of x is a property of each individual particle because it cannot be observed for individual particles. This is my main lesson. Okay, any more questions?
Yakir, may I ask?
Yes.